Hi folks, welcome to part 2 of this week's lesson. So we're going to look at some examples of force and velocity questions. All right, so here we've got a boulder that's being pulled by two people exerting forces of 40 and 60 newtons, and the ropes are attached at the same point, and they're at an angle of 25 degrees. And they want us to determine the equilibrium force. So let's keep in mind what the equilibrium force is as I'm drawing the diagram. Okay, so I'll just represent the boulder by this point since they're attached at the exact same point. All right, and since they're giving us the angle between the two vectors, I know that I should be thinking of these vectors tail to tail. Okay, so let's say this is the smaller vector, the 40 Newton, and there's the 60 Newton. We'll make it a little longer, and they give us the angle between them. All right, so if we add up the total or the resultant vector that's acting on this boulder, we know that it's going to be this vector here, but this is not the vector we're looking for. We're looking for the vector that's equal and opposite to that one there. Okay, that's the equilibrium force. What's the force that's going to counteract the ones that are acting on the boulder? All right, so let's go ahead and solve this here. I'll just draw another diagram to make it a little clearer. Okay, so here I've got my 40 Newton force and I've got my 60 Newton force, and the angle between them is 25 degrees. All right, now we know that when we want to add up two forces together, when they're tail to tail, best thing is to take this vector and move it over. Okay, and then add them tip to tail. So here's my resultant force. I'll call it FR. Okay, and of course the angle between them was 25 degrees, but that's not an angle inside the triangle that I formed. Okay, so here 180 minus 25, because these are parallel since they're the same vector, so we can use our parallel line principle. So let's see, 180, 160, 155. Okay, there we go. And now we have enough information to calculate the resultant force here. Okay, so we'll start the magnitude. Okay, so here just use cosine law. So square root of 60 squared plus 40 squared minus 2 times 60 times 40 times cosine of 155. All right, and let's see what that gives us here. Okay. So square root of 60 squared plus 40 squared minus 2 times 40 times 60 times cos of 155. Okay, and that gives us 97.73. All right. So now we know that the magnitude of our equilibrium force will be 97.73 newtons, all right, because we know that it's going to be equal in magnitude to the resultant force. But what we have left to do is find the direction, all right? So in order to describe the direction, what I'm going to do is I'm going to describe it relative to this 60 Newton force. Why? Well, because there you go. I've got this angle inside the triangle that I can find. Had I had the 40 Newton force here, I would have described the angle relative to that vector. Okay, but since I've got it set up this way, I'll calculate theta here. And again, to avoid even having to think about the ambiguous case of the sine law, I'm going to do as I usually do when I can, and that's use the cosine law. All right. So what do we have? Theta, its opposite side is 40. So that means 40 squared minus 60 squared minus 97.73 squared all over negative 2 times 60 times 97.73. All right. And let's calculate that here. Okay, so cos inverse, open the bracket for the numerator, 40 squared minus 60 squared minus 97.73 squared, close brackets, divided by, open brackets again, negative 2 times 60 times 97.73. All right, and that gives us 9.95. All right, so we could say that the resultant force has a direction of 9.95 degrees from the 60 Newton vector or force towards the 40 Newton force. But that's not the one that I'm trying to describe. I'm trying to describe this vector here, okay, the equilibrant force. All right, but this is where, well, these are just opposites, meaning this whole angle is 180. So if I want to find this angle, let's say I call it phi, well, phi is just going to be 180 minus 9.95. Okay, so phi here is equal to 180 minus 9.95. And of course, we could calculate that in our heads, but let's just be careful. So 180 minus 9.95, and that's 170.05. Oops, 170.05 degrees. Okay, so the way I'm going to describe the equilibrant force, so the equilibrant force is equal to, so the magnitude we know is going to be 97.73 newtons, all right, and the direction is going to be, okay, 170.05 degrees from the 60 Newton force, okay, and this time we're going away from the 40 Newton force, okay, away from the 40 Newton force. Of course, I could have also given these names so that I didn't have to write so much. All right, so just to recap this one here, step number one was to find that resultant force, using what we know about working with vectors given tail to tail when we're adding them up, but then remembering that the equilibrant force was going to be equal and opposite to that resultant force. Okay, so let's move on to the next one. And this is a question that we referenced in that introduction. Okay, so we have this object that's being held up by two strings, and they give us the angles that the strings make with the ceiling. Okay, and then they give us the mass of the piñata. And they want to know what is the tension in each string, and the tension just represents the magnitude of the force in those strings. All right, so again, what I'm going to do is I'm going to draw myself that situational diagram first, okay, and then from there, draw myself a force diagram. Okay, so I've got two strings, and I'll draw them so that kind of shows that the angles are not the same. So we have this smaller angle of 30 here, and then we have this larger angle of 40. Here's our object, and let's take a look at the forces that are acting on this object. Okay, so we have the force due to gravity, which is moving straight down, and then we have the force or the tension in each string. All right. Now, by the way, at this point, I will reference the fact that in physics, you probably would have solved a problem like this differently. Okay, you would have used something called components, and you're certainly welcome to keep doing that if you're comfortable with it. But for those who haven't studied physics, I'd rather only look at one way of solving these problems, and all the problems we're solving can be done with traditional sine law and cosine law trigonometry. Okay, and sometimes right angle trigonometry. So I'm just going to stick with that one method. Okay, so in order to solve this problem, what I'm going to do is I'm going to take these forces, and I know that they have to add up to 0. So since there's 3 of them, I know they're going to have to create a triangle. Okay, so when I'm drawing the force diagram, or the vector diagram, I might as well start with the easiest one, because I know that the force due to gravity just goes straight down. All right, now, I have a little more room on this side than I do on that side, so the next force I'll do is that one there. So I know I'm going to have this force in that direction, and let's see if I can put some information here. And this is where I'm going to draw myself a little horizontal line, which is parallel to the ceiling. Now we're making the assumption here that the ceiling is straight, but we normally make those types of assumptions in mathematics, and this is where I can see that at the tail of that vector, well, hey, 2 parallel lines, another line crossing it. This acute angle has to be equal to that acute angle. So I know this is also going to be 40, and I can do something similar here. That's also going to be 30. So that means that this angle here is 40 degrees from the horizontal. And then, of course, since this was going straight down and this is horizontal, I know that this angle is going to be complementary to that one. So that's just going to be 50 degrees. So look at that. We have an angle inside the triangle. Now, notice I'm not worrying too much about the lengths here. I'm not 100% sure which one's going to be bigger, because in the end, I'm just using this as a guide. And I know that because the object is in equilibrium, that third vector is going to have to close off the triangle. Okay? Now remember what we had. We had that this angle here was 30. And I'm hoping that you can see that, hey, look, another two parallel lines. So if that's 40, this is also 40. And so together, you get 70 degrees. And lo and behold, you have two angles in this triangle. All right? Now let's see what other information you have. Remember, they told us that the mass was 10 kilograms. So that means this representing the force due to gravity, well, I can find its magnitude because we saw that the formula was just 9.8 times the mass. All right? So that means that's just going to be 98 newtons. And look what we have, two angles and a side length. I can solve this triangle. Now, of course, I also have that angle there. We'll see if we need it. Okay. So what are we looking for? We're looking for the tension in each string. Okay. So I'll call this, let's say I call this 1 and I call this 2. So this is going to be the magnitude of T2. And this is going to be the magnitude of T1. Okay? It doesn't matter which you call which. All right? So let's see what we need to calculate T1. Okay, so magnitude of T1 is equal to, well, let's see. Well, can we use cosine law, or do we even have to worry this time? Now remember, when you have an issue with the ambiguous case of the sine law, you only have an issue with the ambiguous case of the sine law when you're working with one angle and two sides. As soon as you know two angles in a triangle, you actually know all three, meaning that there can't be any ambiguity because the triangle, the shape of the triangle is set. So here, I'm definitely going to use the sine law here because I don't have to worry at all about that ambiguous case. Okay, so here it'll be the magnitude of T1 over the sine of its opposite angle, so sine of 50. And then on the other side, well, hey, I know this side length and its opposite angle, so that's going to be 98 over sine of 70 degrees. Okay, and this is nice and easy to solve. Okay, so we can just get the tension in that string. So what do we have? We have 98 times sine 50, and then divided by sine of 70. Okay, and here we have 79.89. Okay, so that's the tension in one of the strings. And then I'm going to do something similar now for T2. Okay, now here, what I want to try to avoid doing, if I can, is using this answer to find the other. Sometimes you have no choice, but I'd rather work with exact values if I can. Okay, so I'm still going to work with this other pair. But of course here, if I need the sine of its opposite angle, it looks like we will need this angle here. So 70 and 50 is 120, so what remains is 60. So here we have magnitude of T2 over sine 60 is equal to, and I'll use the same ratio on the other side, 98 over sine 70. Okay, so the tension in our other string will be given by, okay, so what do we have? We have 98 times sine 60, okay, and then divided by sine of 70, and that gives us 90.32. Okay, and there we have it. We have the information that we need. All right, so just to recap here, step number 1, drew myself a diagram to kind of situate everything. Okay, then I realized I needed to use some angle properties to get the directions of these two tensions, which is equivalent to the direction of the string. Okay, and then from there I had enough information to draw a vector diagram, this closed triangle, and given the mass, I knew one of the side lengths, and then given the angles, I was able to determine 2 and then the third angle in this triangle. All right, so let's move on to a third example. Okay, and this is another thing that I referenced in the introduction. Okay, so it says Jackie is pulling her little brother on a toboggan with a force of 70 newtons, 25 degrees from the ground. Determine the horizontal force exerted on the toboggan. Okay, so you've got your toboggan here. Okay, and you have someone pulling with a force, okay, and the angle 25 degrees from the ground, okay? But of course, likely you'd be interested in the amount of force that's pulling the toboggan horizontally, okay? So let's draw ourselves a diagram here. Here's the ground, here's the force, 25 degrees from the ground, but what we're looking for is we're looking for what we call the component of the force that's only in the horizontal direction. Okay, so if this is the force that's being applied, we'll call this the horizontal force. All right, and what's nice here is that we see that it just creates a right angle triangle. Okay, so in order to determine this horizontal component of the force, we don't even have to use sine or cosine law. In fact, we certainly should not. Okay, now what we do have is we have the magnitude of the force that's being applied. We know that that's 70 newtons. All right, and so this ends up being the hypotenuse of this triangle. So what we're looking for is the adjacent side, hence we're going to be using cosine. Okay, so if we want to determine this here, we have cosine of 25 degrees is equal to the adjacent side, so the magnitude of this horizontal force that we're looking for over the hypotenuse, which is just going to be 70. So that means this horizontal force is equal to 70 times cos 25. Now, before I calculate that, I'd just like to say something here. So when you think about it, what would be the most efficient way of pulling this toboggan? I would imagine you would think, well, not pulling at an angle, but pulling it straight horizontally. Of course, difficult for someone who's much higher than the toboggan, but that would be the most efficient way to pull it. Now, that also makes sense mathematically, because look at this formula. It's 70 times the cosine of the angle. But where does cosine have its maximum? It has its maximum at 0 degrees. Okay? This cos of 0 is equal to 1. So when the angle from the ground is 0, you get the most out of the force that you're exerting. Okay? So the math fits what we expect intuitively. So let's just find this answer quickly here. Okay, so here we've got 70 times cos 25, and that just gives us a 63.44 newtons. All right. So the last example will be a velocity one. Okay. And let's see what's going on here. It says Horaceville is located 800 kilometers directly north of Horace-town. And we've got a wind blowing from the southwest, and the flight should take 4 hours. At what air velocity should the airplane be traveling? Okay, so let's keep in mind what the air velocity represents. The air velocity does not represent the resultant velocity. It represents the velocity that the pilot is going to direct the plane with. Okay, what we want this plane to do is to go from Horace-town, okay, to Horaceville, which is directly north. So what we want is we want the, whoops, it's badly done here. Let's just fix that. Make the diagram decent here. So what we want is we want a vector that goes in the direction. Okay, this is what we want the resultant velocity or the ground velocity to be equal to. Okay, this is the direction we want the plane to actually take. And how do we get this resultant or ground velocity? By adding up the air velocity of the plane with the wind's velocity. Now, because I have more information about the wind velocity, I'm going to draw that one first. So notice here it says from the southwest. So if we take our cardinal plane, it's coming from the southwest. So that means it must be traveling northeast. Now, one thing I notice here is there's no angle given. So this is where we presume that if we just say from the southwest or going towards the northeast, we'll assume that these angles are equivalent. So this is going to be a 45-degree angle. So when you just see northeast, it's assumed that the angle is 45 degrees. Okay, so we have this wind that's traveling at a velocity of at an angle 45 degrees. Okay, and so the air velocity, okay, because we want this to be the resultant, must go in that direction. Okay, so that means it must add, the velocity of the wind plus the air velocity has to add up to your resultant velocity that you want. Okay, so that's often the mistake that's made in a question like this, is misunderstanding which is the ground velocity and which is the air velocity. Okay, so let's put in the information that we know. So we know the velocity of the wind. Okay, its magnitude is 60 kilometers an hour. Okay, so we know that. Well, we have this angle inside the triangle, because this is going straight north. If that's 45 degrees, that'll be 45 degrees. Okay, and what else do we have? Well, we actually have some information about the ground velocity, because it tells us that it has to do the 800 kilometers in 4 hours. Okay, so we have a distance and we have a time, assuming, as we usually do, that these velocities, that these speeds are constant. We can calculate the magnitude of the velocity. So it's 800 kilometers in 4 hours. So we need the speed to be 200 kilometers per hour. Okay. And so now we've got two sides and an angle. Okay. So we're good. So let's take a look at what we're looking for. So we're looking for the air velocity, okay, and we know its opposite angle and the other two sides, so that means we can use cosine law. Okay, air velocity is going to be given by the square root of 200 squared plus 60 squared minus 2 times 200 times 60 times cosine of 45 degrees. All right, let's calculate that. Okay, so square root of 200 squared plus 60 squared minus 2 times 60 times 200 times cosine of 45, and that gives us 163.19. Okay, and that's kilometers per hour. Okay, so that's the magnitude of the velocity, and now we need to find the direction. Well, I notice here that, and maybe I'll draw my diagram a little bigger here because it's a little tough to see. Okay, so here's my resultant, here's my wind, and here's my air velocity. So we know that this is 45. So if I draw my little east-west, because remember, we want to draw a little cardinal plane at the start of this vector. Well, if this is 45, this is also going to be 45. So what I'm going to do is I'm going to calculate this angle in my triangle, all right? And then I'm just going to subtract 45 to get the angle that's north of west. Okay, so let's start by calculating this angle theta here. All right, and again, as I usually do, I'm just going to use the cosine law to spare myself any possible issues. So that's going to be cos inverse of, so if this is the angle I'm looking for, its opposite side is the 200. So it's going to be 200 squared minus 60 squared minus 163.19 squared, all over negative 2 times 60 times 163.19. All right, let's calculate that. Okay, so here we have cos inverse. Open up your bracket for the top, 200 squared minus 60 squared minus 163.19 squared, close brackets, divided by, open up bracket, negative 2 times 60 times 163.19. and we get 119.92. Okay, but of course that's not the angle we're looking for. We're looking for phi here, which is just going to be 119.92 minus this angle of 45. So what does that give us? Minus 45, so that gives us 74.92 degrees. Okay, so our air velocity, so this is the velocity that the pilot is going to direct the plane with, okay, is going to be 163.19 kilometers per hour. So we see that the wind did help us a bit because the plane's going to fly at that speed, but it's going to eventually achieve a speed of 200 kilometers an hour. And for the direction, well, we're going to use this angle here. So we're going to say west 74.92 degrees north. So west 74.92 degrees north. Okay, so again, just to recap this one really quickly, the important thing here was to understand that the resultant or ground velocity needed to be what the plane is actually going to be doing, which is flying directly north to Horaceville, and this ground velocity is made up by adding the wind velocity, and so that must be the air velocity, so that they add up to your resultant. All right, and that's it for these examples.